This video is going to look at numerical integration, and we're going to look at two ways we can do that. One is using the trapezoidal rule, and the second will be using Simpsons rule. So let's start by looking at the trapezoidal rule. Well, first of all, if we go over here to the right, you'll see a graph. If we're trying to find the area under this curve for function f, notice before in the past we would draw our rectangle. We would go up here and we could draw rectangles here to calculate the approximate area under the curve. Well, now notice what happens if we decide to draw a trapezoid. So instead of drawing a line straight across, notice now we're going up at an angle, and if we draw these trapezoids, what's happening to calculating the area? Well, notice when we draw the trapezoid, it is a lot better approximation because we don't have all this either under area, or if we draw the the rectangle above, notice we have all this extra space above. So you can see that here the trapezoid is going to give us a lot better approximation for the area underneath this curve. So that's what we're going to really look at with the trapezoidal rule. It says that we have a function that's continuous on the interval from a to b. Then trapezoidal rule is going to approximate the integral of f of x. And we have the formula is simply b minus a over 2n. And then we're going to evaluate the function at x sub 0. So if we start with x sub 0, which is our a, your lower limit, we're going to plug that into the function. And then we're going to go to our next number, our next term on the interval, x sub 1. We're going to plug that into the function. But notice then, after we evaluate that, we're going to multiply that by 2. And we're going to keep doing so as we go along. We plug in our x sub 2, and that's also multiplied by 2. And everything's going to be multiplied by 2 until we get to the very end when we plug in our x sub n, which would be our upper limit b. Notice once we evaluate that into our function, it is simply multiplied by 1, as well as our first f of x sub 0, which is our f of a. So here, your f of a, your first term, and your last term, f of b, is simply multiplied by 1. It's only all of these other terms in between that are being multiplied by 2. So once we evaluate this, we sum up all of these values and multiply by b minus a over 2n, and that will give us an approximation for the integral. Now you may ask, why would we want to go through all of this numerical integration when we could just simply use our fundamental theorem of calculus and we could just simply integrate? Well, there are several functions out here that we're just not able to find the integral of. For an example, if I gave you something like the integral from 0 to pi sine of x squared dx. We simply do not have an elementary antiderivative that we could evaluate this sine of x squared. So in cases like this where we just do not have an antiderivative, we can use some way numerically to approximate the integral. Okay? So let's look at an example of how we can do that with the function below here. We have 1 over x squared, and this is going to be evaluated from 1 to 2, and they want us to divide this up using 4 trapezoids. So if we start over here, I have the graph, and on my calculator I set my window from 0 to 3 on the x and 0 to 1 on the y. So here we have x equals 1 to 2. So if we start at 1 and we go to 2, well, if we want to divide this into 4 trapezoids, then we're going to take b minus a over n. So we would have our interval of 2 minus 1 over 4. So we end up with 1/4. Now, please do not confuse this formula b minus a over n with the b minus a over 2n. This is different. The b minus a over 2n up here is actually part of the formula for the trapezoidal rule. The b minus a over n that we're using here is to mark off the width of 1/4 for our trapezoids. So if we do that down here, we're going to have widths of 1/4. So we would start here at 1. We could think of this as 4/4. And then we would go to 5/4, 6/4, 7/4, and then of course the last would be 8/4, which would simply be 2. So now if we approximate this, we know that we're going to end up with approximation b minus a, so that would be 2 minus 1 over 2 times n, so that would be 2 times 4. And all of that's going to be multiplied by f evaluated at x sub 0. Now this may be helpful to realize we start here. This is our x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So notice x sub 0 is where we start with, so we would evaluate that at f of 1, and then we would have plus 2 times, okay, remember the formula, the first one is multiplied by 1, everything else is multiplied by 2 until we get to the very end. So then we would have 2 times f of 5/4 plus 2 times f of 6/4 plus 2 times f of 7/4, and then we have plus f of 8/4 or plus f of 2, okay, and remember the first and last is simply multiplied by 1. So our function up here, 1 over x squared, we now need to evaluate our function at each of these points. So we need to plug each of these values in for our x. Okay? So if we do that, we would then simplify this to 2 minus 1 over 2 times 4, so that becomes 1/8. And if we plug 1 in for x, we get 1 squared, so that becomes 1. And then we get 2 times 5/4. Well, if we square 5/4, that's 25 over 16. And if we take the reciprocal, because it's 1 over 25/16, that becomes 16 over 25 plus 2 times, again, 6/4 is the same thing, so that would become 16 over 36 plus 2 times 16 over 49 plus, if we plug a 2 in, that's squared, so that's simply 1/4. So now if we perform all of these calculations and multiply by 1/8, just simply put this into the calculator and you should come up with an approximately 0.50899. So this is an approximation to the area that we would find underneath the curve. All right, we do have another example here, another technique called Simpsons Rule. And if you notice, Simpsons Rule looks very similar. I'm not going to go into the details here, but if you read in your book about this, you can see where this is actually coming from a way that we can actually approximate our function using a quadratic function to approximate this. And again, you can read this in your textbook. But if you look at the formula, it's very similar. I will point out a few differences. It starts out with b minus a over 3n instead of over 2n. And it does start off with multiplying by 1 for the first term, and the very last term is multiplied by 1. But you'll notice the other terms in between alternate from being multiplied by 4, 2, 4, 2, and then the next to the last is multiplied by 4, and then the very last term is multiplied by 1. Now, in order for this to work out appropriately, you'll notice for Simpsons Rule, your n has to be even. Okay, so the number of intervals has to be even. If you're using n equals an odd number, you cannot use Simpsons rule. You would have to use the trapezoidal rule. So just to look at this, I want to use the exact same integral we did before, the 1 over x squared, and I want to still use n equals 4. But now let's see what happens if we use the Simpsons rule. Well, if we plug in here, we're going to have the same thing as we did before. Of course, if we go from 1 to 2, we're still going to break this into 4 trapezoids, so to speak. Our intervals would be 4. Okay, so we would start and we would go from 4/4 to 5/4, 6/4, 7/4, and then 8/4, which is 2. So we're still going to divide this up into the same number of intervals, except for now our approximation, we would have b minus a, so that's 2 minus 1 over 3 times 4, and then that's going to be multiplied where we're going to evaluate each of our terms again. And keep in mind we start with x sub 0, x sub 1, x sub 2, x sub 3, all the way up to x sub 4. So if we do that with our example, then we would simply have f evaluated at 1 plus function f evaluated at 5/4. Now, whoops, I made a mistake here. We start with 4. So we started with 1, and then we went to 4 times f of 5/4 plus 2 times f of 6/4 plus 4 times f of 7/4 plus, now notice here we ended with 4 times f of 7/4 plus our f of 2. And again, realize that we multiplied by 1, and then we alternated 4 times 2 times 4 for the terms in between. So then from here, just like we did before, we would evaluate. We're going to end up with 1/12 here being multiplied by 1 plus 4 times 16 over 25 plus 2 times 16 over 36 plus 4 times 16 over 49 plus 1/4. And if we perform all the calculations here, we will come up with approximately 0.50042. So if you notice, that's still pretty close to what we calculated above. We came up with 0.50899. So both of these are pretty good approximations. Now, for this particular example, we were looking at calculating the integral of 1 over x squared from 1 to 2. Well, we know that we can actually integrate this. If we think of this as x to the negative 2 dx, well, if we integrate, we would become x to the negative 1, increase your exponent by 1, divided by negative 1, and we want to evaluate this from 1 to 2. So we would have negative 1 over x, make our exponent positive. So now if we evaluate this, plug in our 2, we would have negative 1/2 minus, plugging in the lower limit, we would have a negative 1 over 1. So we really have a negative 1/2 plus 1, so that equals 1/2. And this here is the exact answer. So whereas above we were looking at approximations, if we can actually integrate this, we know that we'll come up with the exact answer. So that gives us the exact area under the curve. And you can tell that from our approximations up here, 0.50042, that is very close to 1/2, as well as with the trapezoidal rule when we came up with 0.50899. So you can see that these two techniques for numerical integration are pretty accurate if we had a problem that we were not able to integrate. Now, there's ways that we can look at this, and I'm not going to look at it at this point in time, but there's formulas that we can use to calculate how many intervals do we need to be so accurate. So for example, here we were using n equals 4. So imagine what would happen if we let n equal 10 or 20. Now we don't want to do more calculations than needed, so there are formulas that you can use to determine how many intervals we need to use based on how accurate we want our answer to be. So keep in mind, if there's formulas out there that we're not able to integrate, we can always use Trapezoidal Rule or Simpsons Rule, although Simpsons Rule, remember, you have to have a number that is even for your intervals.